Okay, we're going to be talking about finding limits, just an introduction to limits today, and we're going to do that from a graphical perspective. This works well in tables as well on your graphing calculator, but the graph really reveals a big part of the picture. So I've got five, as you can see on here on this HarCulator program, I have a function stack, and I have five functions stored. I'm going to start with this number 5. And you get a good view of what these look like. So our first function is the rational expression x minus 3 on x squared minus 9. And we are actually looking to find the limit of this as x approaches 3. So we would look at this as perhaps limit as x approaches 3 of this function. And so let's go ahead and take a look at the graph of this guy. Try this. And here we go. And our eyes are immediately on this. If we have any experience here with, if we have any experience with limits whatsoever on this, our eyes are drawn to -3 over in here. However, we're looking for the limit as x approaches 3. And when I look at the limit as x approaches 3, it appears as though we have left hand and right hand agreement. In other words, as we come in from the left and come in from the right, we are bearing down on the same value. So if you had this graphed on your TI, you would just graph this as y1 equals, and then you could go ahead and enter trace on your calculator and just enter a value close to 3. In fact, let's go ahead and just enter 3. And as I have 3 entered here, you can see that that's a division by 0. So 3 is apparently a hole in the graph. So since I have left and right hand agreement, though, we should have a limit at 3. So I can just go ahead and, as I hit trace on my TI, I could just enter 3.0001, for instance, and see what happens just barely to the right of 3. And I see that just barely to the right of 3, we are at 0.166663889. And then I would want to know what's happening as we move just a little bit to the left of 3. So a little bit to the left of 3, maybe 2.9999. I see I'm also at 0.166669444, and therefore I would like to suggest that we are definitely in agreement from the left and the right, and we are somewhere close to 0.16, and maybe the 6 repeats, but that isn't necessarily so, but it sure is close to that value. And that's what we're looking for now. It'll be a later study of ours in order to figure out what the exact value of that limit is. But for right now, from a graphical perspective, or if you used table, we're pretty darn close to 0.16 with the 6 repeating. Okay. Okay, so let's take a look at another one. This in our book is number 9, very similar approach. So I've pre-saved number 9, and what you're looking at up here is Excel speak for e to the 2x. This is just e to the 2x minus 1 on x, and what we're finding on this one is the limit as x approaches 0. So we'll go ahead and take a look at this guy. The limit as x approaches 0. And once again, if I look at x is 0, it appears as from the left, as I'm coming up to that and coming back from the right, that we have some agreement, and it sure looks like it's narrowing in on 2. So the first thought might be, well, let's see, since we have left and right hand agreement, let's see what happens when we put 2 in. And you would just do trace, hit 2 on your calculator, and hit enter. And you would see, whoops, I'm sorry. We're finding as x equals 0. We put in 0 and we realize, oh, that is a division by 0. Well, it only takes a moment to realize that we probably could have recognized that, because e to the 0th minus 1 is 1 minus 1, 0 on 0. We've got a situation where an old Ghostbusters reference here. 0 on 0 mathematically is the equivalence to crossing the beams mathematically. So the function does not exist at 0, but it sure appears to have left and right hand agreement at 0. So once again, I'm just going to put in a value close to 0, perhaps negative 0.0001, and I see that I get 1.9998-ish. And that's very, very close to 2, so I'm going to go just the other side of 0, and I get 0.0001, for instance. And I see, well, it looks like it's just on the other side, just above 2, so there's a very good chance that our limit is actually just plain 2. Does that mean it's exactly 2? It may be, but it certainly doesn't have to be. Again, that's for a later discussion. Come back in 2 days and we'll talk about how we find out what it is exactly. Okay, next problem, number 17, pre-stored again. Number 17, we can certainly see what this is, sine of x on x, and the book asks us to find this limit as x approaches 0. And a real quick inspection here, if I put 0 in for x, I get sine of 0, 0 on 0, 0 on 0. As I just mentioned, we would refer to that as the Ghostbusters terminology of crossing the beams, which all life as we know it ceases to exist. That's the mathematical equivalence of that. So let's take a look at this guy's graph as we fight a little bit of technology here. Okay, real quickly, if I was to put in 0, we see we have a division by 0, which we've already checked, and we knew that that was going to be the case. But once again, from the left, from the right, it sure looks like we are agreeing on a value at 0. So I put in a value close to 0, maybe negative 0.0001. Try that again. Negative 0.0001. And I get something very, very close to 1. Place a value on the other side, positive 0.0001. And very, very close to 1. And you may say, well, maybe it just never quite gets to 1, and you may very well be right. But I do notice the tendency on both sides of the curve as it's approaching 0 is upward, so I suspect there's a good possibility that our limit of this function as x approaches 0 is 1. Okay, let's take a look at problem number 39. For problem number 39, this is a really, really cool graph. Cosine of 1 on x, they're once again asking for our limit as x approaches 0. And the graph of cosine is just fine at 0. It exists, it's 1, but this is 1 on 0 we're looking for. So cosine isn't the real issue. The real issue here is I can't put 0 in for x because I can't take 1 and divide by 0. So let's go ahead and take a look at what this graph looks like. Okay, so nice simple looking graph from negative 10 until it gets over to about 1, and then things seem to go crazy around 0, and that's what we're looking for. We'd like to know what's happening at 0, so maybe the first thing I would do is try to put in 0, trace 0, and once again we get division of 0, which is expected. So I have to look around to the sides. But I want to get an idea if we have left and right hand behavior, if we have left and right hand agreement at 0. So I'm going to go ahead and narrow in on this a little bit. I'm going to set my x min to negative 1. I'm going to set my x max to be positive 1 and look a little bit closer. By the way, this is in radian measure. I think I'm going to zoom in on this a little bit and add a couple decimals so we know where we're at here. And I see, boy, all heck is breaking loose around 0, but maybe if I look in a little bit closer, I can get an idea of what's going on here. So maybe I'll change my x min to negative zero point 0.1 and my x max to positive zero point 0.1. And doesn't really clear things up very much, but I can continue this search for a while. I'm going to go one more increment in, and I'm going to go negative 0.01 to positive 0.01. Maybe that'll give me an idea what's happening at 0. Yikes. What we have here is a graph that is oscillating more and more rapidly as we approach between the fixed values of negative 1 and 1. And that is one of the occurrences where we do not have, where there is no limit as that oscillation goes faster and faster. And if we think about this for a moment, what's happening to just little old 1 over x as x is approaching 0? If I have 1 over 1 millionth, that's a million. 1 over 1 trillionth, that's a trillion. As x gets closer and closer to 0, the values, the argument of cosine is just exploding to huger and huger values, and it's trying to run through its cycle much, much faster and faster and faster and faster because we're approaching infinity here at a very fast rate. This thing is going to just continue to oscillate throughout this faster and faster as we approach 0. So that is a case where there is no limit as we are oscillating between two fixed values, namely positive 1 and negative 1. So really cool graph. Let's see how much that slows me down clearing off that smartboard drawing as we move on to the next function. So that, once again, there is no limit to that function as x approaches 0. Okay, let's go back. And let's look at one more problem. Maybe not quite as cool, but pretty applicable here. Here we have the rational expression, x minus 1 on x squared minus 4x plus 3. And for this problem, they're asking for us to find the limit as x approaches 1. And immediately I can see in the numerator, we've got some challenges as x approaches 1. This is 0, but that's okay. However, when x is 1 in the denominator, I get 1 squared 1 minus 4, negative 3, plus 3, 0. This is tending at 1 to be 0 on 0. Once again, we cross the beams, and that's what limits are mostly about. So let's take a look at the graph, see what's happening at 1. Need to zoom out on this guy. I'm going to go back out to negative 10 to 10 both directions and maybe take off my decimals here. Okay, and our eyes are immediately drawn to 3 because of the asymptote. And if the question asked what's happening, what's the limit at 3, we would say there is no limit. However, once again, as I mentioned earlier, we're trying to find the limit of this function as x approaches 1. And I see 1 looks pretty tame. Once again, it looks like our left hand and right hand approaches are in consensus to some value. So we may, if we hadn't already checked it, be tempted then to just go ahead and try putting 1 in here. And we see that we have a division by 0, which of course we already knew. So once again, what do? We just choose something very, very close to 1, like 0.9999. And I see I am at negative 0.49997. That's pretty revealing. Let's take a look just on the other side of 1 at 1.0001. I'm just on the other side of negative 0.5, so I suspect, I'm not certain, but I suspect our limit is 0.5. Might it be a little bit different? It might be a little bit different, but I suspect there's probably good reason to believe that it is exactly 1/2 or 0.5. That again, that's left for tomorrow's lesson. So you want to come back and find out how we show that this is exactly 1/2. I'm sure you're going to be thrilled to find out the answer to that, and it's going to be a little easier than you might think.